Hi guys, I'm Bohan Fang, and here's my teammate Jiahe, Yijie, and Haoyang. Our topic is basically about AN accelerated network intrusion detection system. Before introducing our product, let's first take a look at the short video about the airport security check.
This is a short cartoon about security check in airport.
Hi, here's my ID.
Okay, I will check it. Here is your ID.
Thank you.
Please proceed to the security checkpoint ahead and queue for screening.
Okay, I got it. Please place your laptop, umbrella, power bank into the tray. Remove your coat and shoes, and ensure your pockets are empty. Okay. Everything is all clear. Please proceed ahead and wait to pass through the metal detector. Okay, thank you.
Please following the posture on the guide and walk through the metal detector. You are all set. Please wait and take all your baggage.
Okay, thank you and have a nice day, sir.
However, if there are some risks be detected,
Your luggage has triggered an alarm during the security check and must undergo either a 3D CT scan or a manual bag inspection.
Will it take a long time?
Yes, please wait patiently until the inspection is complete.
Okay,
if a weapon is found during the inspection,
You have a weapon in your bag. Put your hands on your head and squat down.
but because the equipment is so expensive, only a few major airports are equipped with 3D CT scanners. In such cases, luggage carrying a weapon may pass through a standard X-ray machine without being detected, posing a serious security risk. And if it's a weekend or during peak travel season, when passenger traffic at the airport is very high,
Now that passenger traffic is heavy, to speed things up, please keep your shoes and laptop on. Send only your backpack through the X-ray scanner and walk straight through the metal detector.
okay.
in this situation, if the machine fails to detect a weapon in your bag, then danger is imminent. This is a short
Okay, so just similar to the airport security check, our computer every day do the same thing. When the data in and out through the internet, it will have some risks. Typically, we have a firewall which could help us, just like the basic security check. It could detect some normal risk on the internet. However, if they have some malicious traffic which could bypass the firewall by using some non-standard ports to launch some attacks, thus the firewall is not really safe. And if we have some malformed packet due to some encrypted traffic, we need manual access from the administrator. It's really time consuming and really high cost on the human power. And everyone knows human will make some mistakes, so traditional network intrusion detection system need to be updated. Moreover, traditional NIDS software is just single-threaded, so it will easily losing packet during the network peak. Thus, the malicious attack could bypass the detection. And if this malicious attack could not be detected, your computer will be attacked and hacked. Your information and property might be at a really high risk, and it's just like failing to detect a weapon during the security check, and the consequence could be catastrophic. And actually, in this day and age, it already have a really good NIDS software tools. It's called Node. It's an open source, rule-based, plug-friendly tools. The main mechanism is that when the data go in, you will check the header information, scan the content, and find some risks, and give you some warning. So the safe packet will go in, and if you miss some risks, it will warn you. But the traditional node also have some defect. The first is that it still be the single-threaded design. It could not detect all the intrusion in real time under the higher traffic load. And second is unable to perform the wide speed packet inspection on the 1 gigabit and 10 gigabit link. But in this day and age, this 1 gigabit and 10 gigabit link is what we want. So it's really, really bottleneck. And here is a DPI market size. You can find in 2023, the market size of DPI is 26.8 billion, and in the prediction, it will increase at a rate 25.1% every year. And you can find a lot of company use this node. The really big one is the technical and the education in these two areas. And you can find really, really big company, which is famous: Cisco, Palo Alto, Fortinet, Juniper, Checkpoint, and some university, Boston, Arizona, Northeastern, and Johns Hopkins. So if we could find a way to improve the traditional node or even create some new tools, we can earn a lot of money on the DPI market size, because this market size is really huge and every company needs this for their network safety. So here is our main competitor. You can find it's Palo Alto, Fortinet, Cisco, and Checkpoint. But the only one we need to mention is Cisco, because only Cisco and their products from the source fire, they use something from this node. Their 3D system is a commercial DPI product built on the Node engine. So it will perform full packet inspection and rule matching on the general purpose CPU or virtualized platform. So as the traffic volume and the rule set size grow, the resource consumption scale will be exponentially. So in high bandwidth scenario, you must provision every more CPU cores, memory, and input-output to sustain the linearity detection. The software stack, context switch, and the kernel communication overhead will further drive up the power draw and the hardware cost. This will create an event bottleneck in the latency and throughput, and it's still high cost. So by contrast, our ANN-based hardware accelerator offload the pattern recognition and feature extraction to dedicated circuit that purpose in the parallel at the silicon level. It will achieving low detection latency, higher throughput, and superior performance per watt. And although upfront chip design and validation cost is still not really cheap, the mass-produced unit deliver better cost and performance metrics than the pure software solution. That's what the Cisco source file do. So overall, in the high traffic, we will have a higher performance, and our AN accelerated DPI design should show a clear advantage. So next, I will let our teammate Jiahe to introduce in detail about the software and the hardware of this node.
This is how Snow system works originally, and I will analyze the drawbacks of the orange Snow system. The first one is low throughput. Since Snow an IDS can run only as a single-threaded application that may not be able to detect all attacks in real time in networks with high traffic load. And furthermore, as you can see, all attacks needs to be matched against thousands of rules in the detection engine, which leads to large overheads for the CPU. The second one is it can only identify attack patterns based on known rules. It doesn't work when it comes to zero-day attack and new attack methods. And to overcome the problem caused by precise pattern matching of Snow system, the use of machine learning and AI methods has become a popular trend in recent years. Major tech firms such as Microsoft and Cisco are actively developing AI-enabled security solutions that offer real-time monitoring and analysis capabilities, thus enhancing the effectiveness of intrusion detection system. And this is one of ANN-based optimization solution using software. It has two layers. The first layer is not system to detect signature-based patterns. If it's not matching, ANN module will analyze the anomalous traffic. So now with the help of ANN module, anomaly-based detection of snow system is no longer a big problem. However, low speed and throughput are still big problems in software. The cost for snow system to have wire speed packet processing and real-time detection of malicious packets still exists. Also, the training and inference process of ANN module can consume a lot of CPU resources. So our product is ANN power hardware optimization of Snow system. We designed a dedicated neural processing module to implement ANN model in hardware in our system. This is our ASIC IP, since it is a specific circuit designed for ANN module and deploying on NetFPGA platform. The latency of our system can be very low and it can be operated in a wire speed. And all the data training process is completed in software. So hardware resources used in our product is much fewer than pure software solution, which can be cheaper. And to overcome the throughput problem, our network intrusion detection system is based on NetFPGA hardware. Even though the board we are using coming from 25 years ago, it can still achieve a bandwidth of 8 gigabits. Some newer NetFPGAs, such as NetFPGA Sumi, can achieve a bandwidth of 100 gigabits. So here comes to the advantages of our system: fast speed, strong scalability, high adaptability and flexibility, and last but not least, being able to learn further. This is the overview of our system. When a packet comes in, packet will be first extracted, and the detail of how we extract the packet will be introduced later. Then the packet combined with the feature will go to the ARM CPU, and we will forward the feature to the hardware accelerator to process. If it indicates that it is a malicious packet, then the packet will be dropped. And now comes to the overview of our ANN accelerator. The weights and the bias have already quantized into initial format to reduce hardware computation costs, and they are hard-coded into the on-chip RAM. Initially, the input feature vector will be forwarded from CPU data memory to ANN's input cache. Then this feature will be multiplied and accumulated with the weights and the bias in the ANN module. And the results generated by the ANN module will then send to the result cache for the next hidden layer computation. And all the steps of the process are performed correctly thanks to the FSM control unit. So this is the data pre-processing part. For the handler, we extract the 5-tuple information. For the payload, we apply the ingredient technique to segment it. Then we hash both handler and the payload segments to form a feature vector. The dataset used for training is acquired by using TCP/TOM to capture real-time network traffic. However, since malicious traffic accounts for a very small portion, we also incorporated the intrusion detection evaluation dataset. And finally, labels are generated based on snow rules. So why our product stands out? As you can see in this chart, compared to traditional snow-based IDS solution, our NetFPGA plus ANN system achieves significantly higher throughput at a lower cost, making it being faster and cheaper. So this is the technical explanation of our product. And next, my teammate Haoyang and Yijie will show the demo video of our product to let you know how our system works.
For the implementation of the ANN, the first thing is to conject the data set. We use TCP/DOM to capture the real network traffic. Cause here is just an example. So I set 10 numbers of packets. Cause if the number is too large, it will take a really long time. and then is use snout to analyze the capture.pcap, which we just captured before. And we can see the snout log file. As you can see, the date, time, malicious information, as well as the protocol IP port, it will be recorded in the snout log. And because of the data packets which of the data we need is only the factorial and the payload of the packet, so we need a Python script to pre-process the data to get the final data set. Here we use Jiahe to pre-process the data, and then we get the labeled data set by the .csv file before, as well as the snout alert log to label the data line, which is malicious or normal, which is something like here, source IP, destination IP, source port, destination port, protocol, payload, hexagonal format, and label. 0 means normal, and 1 means malicious. The snout log is saved here because the malicious data packet in daily life is really low, so here we incorporated the CIC IDS 2017 data set as part of our data set. And then is the training of the ANN, cause the data packets should be pre-processed before as the feature vector. So first, this function is used to extract the features from the data packet. We use 8 bytes n-grain sliding window to process the payload, and each n-grain is hashed file murmur hash to get an index between 0 to 255, and this 256 histogram counts how often each bin index appears, and the function is load the dataset from CSV, and then we define a simple feed-forward neural network, which the input is 256, and the hidden layer has 3 neurons, and the output is 1. Cause the because the resources of the hardware is limited, so we quantize the floats 32 ways to int 8 to reduce the overhead. And in the main function, we use all of the functions before. And finally save all the hidden ways BIOS and the output ways as well as BIOS into the TXT, which will be used later. Cause for the convenience, we use Google Colab to the code. Here we totally have 11,000 data lines. As you can see, as time went by, the accuracy is larger and larger, and first original weights and bars is float 32, and after quantizing, it will be int 8 to reduce hardware overlays, and all the weights and the bars are saved into the txt files. And next is to simulate the forward process of the ANN. Here's the ANN forward simulation file. We define the input layer as 256, and the hidden side layer has 3 neurons, and output is only 1. And the ungrained size is 8 bytes. So first we need memory hash function to pre-process the ungrained to the bin histogram, and then we should extract the features from the flow metadata. First, we concatenate the factorial into a string, and then convert hex payload into binary bytes. Then append the header and the payload, extract the 8-byte engrams and counter-currencies. Finally, we normalize the 256 dimensional histogram to form a feature factor. And then it's load the model rates as well as the feature factor function. In this main function, we later input extract the feature and load the parameter and calculate the hidden as well as output data to get a prediction. And then we can simulate the ANN forward process by running this code. So we should input the factorial information as well as the payload, which is hexadecimal format. We can just copy the a random data from the dataset. So as you can see, this data packet is normal. 0 is normal. And here the prediction of result is normal as well. We can run this several times. This one is malicious. And the prediction is malicious as well. And this is normal. The prediction of result is normal as well. And this file Verilog code is the forward process of the ANN, which implement by Verilog. The model is parameterized, so input size and hidden size can be modified. And here is the state definition. And the idle state is to wait for start signal, and calculate hidden is to compute hidden layer output, and calculate output is to compute final output, and the down state means signal inference completion.
Next, I will demonstrate the operation of our system on the NetApp PGA. First, I have downloaded the compiled bitstream file to the NetApp PGA, and then use the reloading script to load the previously trained weights into the pre-allocated register. We can see the weight loading completed. After that, I use TCP down to capture packets at the receiver side in real time to showcase the detection and interception capabilities. We use the port 6547. And the NetApp is ready to capture the packet from the N1 to N0. And in the node N0, we use netcat to listening the message from the other ports. The port is 4560. And in N1 port node, we first send a packet containing normal data to the host with the IP address 10.0.16.3 via port 4567. We send a hello. We can see the NetApp PGA successfully received on the receiver side and captured it successfully. And in zero node, the hello is received by the host. And we use another port. Then we send a package containing malicious content. Some SQL injection attacks may include large numbers of keywords such as uniselect and this stuff. So this time I send a package containing the word select. Okay, look at the payload of this package. We can see the packet is successfully intercepted and dropped by the NetApp PGA. So this proves that our system is effective.
I will show how our program run and the result of our application. So first, we download the bit file into the NetApp PGA. And start the RKD. We can try to ping. And there is no problem of connection. There is 3 Python scripts, and first we start the server to listen. And use the client to send about 1000 packets to the server. And after the server receives all the packets, we can find that here is have captured some information and saved as txt format. we can think that uh, here is all the binary data of the um, information of packet as well as the prediction. We can use the analyze Python script to summarize the result. And we can see that about in 450 malicious packets, we only received 37, and the accuracy of the malicious packet is 91.8%, and the total accuracy of our program is 94.2%.
And this is our business plan. Our products are mainly sold to small and medium-sized enterprises and industrial edge network customers, and we provide them with subscription service such as rule updates and ANN model optimization to obtain stable profits. For network security vendors and security equipment vendors, we authorize the use of our platform as an embedded intelligent detection module and charge a one-time or volume-based fee according to the authorization agreement.